Java files in that application and more than 1 million lines of code, which was built over multiple generations of Java technology over a decade, from SOAP to Jaxby to so on. And over a year of ongoing manual migration effort, they're trying to migrate this to cloud, actually, to microservices, what is now known as microservices. So they're trying to refactor this code. They're trying to understand this code and refactor this code so that they can migrate it over, which is known as application modernization. And the results with our AI for code modernization effort resulted in recommendations and validation of code factoring within 4 weeks versus a year that they've been at it. It recommended 25 plus partitions or microservices consisting of around 450 plus classes, leveraging both runtime and data dependency analysis. And interestingly, just as a side effect, it also exposed much of the dead code, which had never been exercised, which contaminates a lot of the previous application as well. So I wanted to point this out and bring this home because it has real implications on what we talked about very early on, that IEEE Spectrum captured as AI's next challenge, modernizing legacy infrastructure. And it has real implications of how AI can help in that area. So just to close this chapter, obviously data sets like CodeNet can bring together algorithms and compute to give rise to a technology with the AI for code algorithmic stack and really unleash a business value for use cases like modernizing legacy code and boost developer productivity as we really beef up this code, this stack more and more to give rise to significant productivities for software developers as AI continues to disrupt and make better the software developer ecosystem as well. Let me see how I'm doing on time. 10:35. Okay, so I'm going to stop at 10:50, I hope, or so, actually, and then take questions. So I'm going to skim through this more quickly. I think the next chapter I was going to talk about is what's next in hardware. And I wanted to start this because we are proud of this. You don't hear about it as much because things that continue to work, you don't hear about them as much. And this has been my history. And for some of the people who are on this call, their history as well. And we are very proud of it. You probably used IBM systems today when you woke up. You don't realize it, but you likely did, because it actually processes, IBM System Z processes roughly by many measures, $3 trillion in daily commercial transactions, 30 billion transactions per day. 90% of all credit card transactions run through IBM systems. 92 of the world's top 100 banks use it. 23 of the top 25 airlines use it. And 10 of the world's top 10 insurance use it. So all of the top 10 insurers use it. And 75% of Fortune 500 companies use it. So what's behind it? And what is being done from a hardware point of view, and where is hardware going in terms of AI and hardware sort of getting married together? And this is not just about GPUs, actually. This is going to unleash new use cases that are going to impact the lives of you and I and others as we move forward. Because as I said, you probably used the IBM systems today, and it has implications on what kind of hardware will be coming down as we move forward. We believe hardware will become a lot more real time as we move forward, whether it is on edge or in the data center. It will not be just about training AI models. It really will be about, obviously training AI models that there are many companies around, including NVIDIA and others who are focused on this a whole lot, but it will also be about infusing AI as part of the business processes. And my ICCAD talk focused on this a lot more, on engineering the future of AI for enterprises. What are the issues and challenges and opportunities that enterprises are facing for intersecting AI with the business processes, which means AI need to become a lot more real time. And recently we launched, just last week, we launched IBM Talem processor. Its claim to fame is performance and scale. embedded accelerators, not just accelerators that have existed, but a new accelerator we brought in, and I'm going to take you through very briefly descriptions of it. It's the AI accelerator and what are its specs. All married with security and really unmatched reliability and availability. Just to give you a peek into this, the single chip module has 8 cores, runs at roughly 5+ gigahertz, 256 megabytes of cache, with embedded AI accelerators in 7 nanometer technology. And the dual chip module, which I'll show you the picture of in the next slide, contains roughly around 22.5 billion transistors and 19 miles of wire on 17 metal layers. So this is really a feat of engineering in itself, with the complexity that it captures and with the use cases it is going to enable. So building a large-scale system connecting up to 32 chips. The single chip I just talked about, dual chip module, has 512 MB of cache. 4-socket drawer has 8 chips with 2 gigabytes of cache. And a 4-drawer system has 32 chips and 8 gigabytes of cache. And it really results in an overall performance improvement from its previous versions of 40% socket performance growth. But more importantly, I wanted to talk today about how AI is intersecting hardware with some of the more interesting use cases in addition to training the model and the GPUs themselves. So, really, world-class AI needs a world-class AI inferencing platform to enable use cases for enterprise workloads. What are those enterprise workloads that impact all of us on a daily basis? As the transactions are happening, enabling use cases like fraud detection, which is real time. This is not about I'm sampling some of the transactions and I have some thresholding based rules. And while you are trying to swipe your credit card at the grocery store, it comes up that, and it annoys you many times as well. Those are what I'll call rule-based systems with thresholding. AI systems, if they need to have these real-time capabilities, the performance requirements are extremely tight. And we'll talk about some of the numbers of latencies that are needed in this area. So, really business insights like fraud detection, when the fraud is happening, customer behavior prediction, when the customers are actually doing purchases, to be able to offer them certain extra benefits at that time, because later on is more annoying than when you are actually making the transaction, you are in the middle of it. Supply chain optimization. And from an intelligent infrastructure point of view, workload placement, database query plans, and anomaly detection for security. So cybersecurity in itself, a popular topic these days and extremely critical as well for the decade which is ahead of us. So, really maximize AI value with low and consistent latency, enabling real-time applications, as I talked about, minimizing security exposure for sensitive data, and inference tasks that are directly embedded into the transaction workload while that transaction is taking place, because this is the platform where 90% of your credit card transactions are going through, and $3 trillion of business transactions or business transactions being done on a daily basis. So let's take a look at this, briefly, a peek under it. It's a centralized on-chip accelerator shared by all cores, very low and consistent inference latency, compute capacity for utilization at scale. It can run a variety of AI models ranging from traditional ML models to RNNs and CNNs. It has security integrated as part of it to provide enterprise-grade memory virtualization and protection, and extensibility with future firmware and hardware updates as well was planned for it as a design point. And this was really collaboratively done across our IBM systems team and IBM research. A truly phenomenal partnership for us. So in terms of new neural network processing assist functions, it's got memory-to-memory CISC instruction that was built in for it, operates directly on the tensor data in the user space, supports matrix multiplications, convolutions, pooling, activation functions, firmware running on the core itself, and an AI accelerator. an enterprise class availability from a availability and a security point of view. And here I'm showing, obviously, this is the core, and this is the accelerator, and there is a high-speed communication actually between them as well. So in aggregate, it offers greater than 6 teraflops of performance per chip, over 200 teraflops on 32-chip system. I won't go into the detail of this. You can read it online as well. Christian Jacobi, the chief architect of it, has a very nice talk on YouTube that you can certainly hear to get a lot more detail on it. So let me just skip through. And it seamlessly integrate AI into existing enterprise workload stacks. You can build and train anywhere you like, actually. You don't have to build and train, obviously, on this platform. You build and train anywhere you like. It supports Keras, PyTorch, MATLAB, MXNet, TensorFlow, obviously, and Onyx format. And you can deploy on System C, which is IBM system, for applications like banking, finance, insurance, retail, hospitality, transportation, and beyond. Supports languages like Java, Python, COBOL, and C and C++, with obviously a complete stack of app servers and platforms, database and operating systems, and beyond. So we are very proud of this because it brings hardware to a new level in terms of its performance. And let's take a look at what does that mean. In terms of the performance, one chip system offers you 116,000 inferences at 1.1 millisecond. And that's the kind of latency that you've got to enable a real-time transaction, because the quota that you get for inference, there are many things happening in the transaction, by the way, including network latency. The quota that you get is actually almost sub 1 millisecond. And in 2 chips, we can actually do better in terms of throughput of the system. And with 32-chip system, we can do 3.5 million inferences at 1.2 millisecond each. So that's the kind of performance you are looking at to enable a RNN multi-layer model for credit card fraud, built with one of the global banks, one of our clients. It's a proxy model developed by that global bank. And this is the kind of performance that we are able to get with this in enabling some of the use cases that I talked about. I'm going to quickly, actually, I would like to go to, I'm going to skip quantum because it's certainly a very important topic, but go out of the door, not at all, actually, because there's a lot of knowledge embedded in that. And if one thing I've learned in AI, it is about subject matter expertise. The only way AI is ever going to succeed is if we actually really teach it the subject matter expertise as well, which comes from these traditional systems. And finally, I would say RTL testing or AI with testing. And I know Raviv himself has been actually active in this area with techniques like fuzzing and others. And we have written papers on software testing as well. But those need to come together. And I believe that's why I'm emphasizing more and more on the front end part of it, while I see focus more and more on the later part of it, on a lot of excitement on reinforcement learning and floor planning. Great, phenomenal, actually. But my problem is front end. And if you ask anyone doing a chip project today, where will they point to? Actually, they'll say, I suffer on logic design, I suffer on specification, I suffer on testing, I suffer on verification, and rest of the pieces, yep, I can make it better, I got it. But so I would really challenge the team to focus a lot more on that. And I would argue, so one of the
I hate to interrupt you, but should we leave some time for questions?
Yeah, I'm just going to wrap in 30 seconds, actually. So we've been having some discussions with Andrew from Thilo's team, NSF AI Center, which was sanctioned very recently, on some of these topics, and you should hear a lot more about it. A good question is, where will the data come from? You need data to train it. And I did a quick search. I and some others did a quick search on GitHub for logic design code. We found greater than 10,000 repositories on GitHub. I did some quick sampling of the repos. I would estimate, again, I need to verify it, roughly to be greater than 10 million lines of code. Out of those, Verilog repositories were dominant, followed by system Verilogs, followed by VHDL, and this is GitHub only. That data is unlikely to come from industries of the world because they're not putting their Verilog in open. So one of the ideas could be enhanced CodeNet or something like CodeNet with hardware description languages and hardware designs. Lot more information needs to come together to give rise to really techniques like these, which address one of the key bottlenecks that we talk about sort of really upfront on logic design and that phase. So I'm going to stop there for the time being and take any questions. So I apologize for it's been a good discussion on my side, but I'm happy to take questions actually now.
Great. So let's stop sharing, and then I'll allow the Q&A.
Yep.
Okay. Now, if you want to ask a question, all you need to do is just click on the button, click here to speak, and then you can ask a question. So waiting for your questions, and you may also write your question, but you are mostly invited to click on the button where written click here to speak and ask your question directly. Oh, sorry.
Are people able to speak?
I hope they just need to click on the button. So in the meanwhile, let me ask a question. So you were pointing, and this was very interesting, that most of the work is done on the lower level, and the bottlenecks are at the high.
Raviv, I lost you actually. Raviv, I can't hear you.
Can you hear me again? Can you hear me now?
I can hear you now.
Okay, sorry. By the way, I don't know if you are able, if people in the audience are able to press the screen share or the closed Q&A. Please don't press them. It should not be allowed for the audience, but let's go on. So my question was, you are pointing that the bottlenecks are at the higher level. And so what are the key enabler to do something meaningful in this area in your view?
I would really say, so first of all, I think we need to look at, I think one thing I already pointed out, we need to look at a reasonable data set, curate a data set as a community together. And I don't have an answer for it. Andrew and some others and I have been discussing this, and I can promise you this. I'm going to bring, I'll do my best to bring the community together because this is an important topic. Second one, so the first one is, get some of the data together and see where we are with respect to that data. Second one will be start focusing on, I would say, things that can be accomplished. I wouldn't say much easier, but where we have a better shot. And I believe AI and testing together, hardware testing together, we have a good shot at this. AI and potentially debug, the RTL debug is another one where we might have a good shot at it as well. And again, I think I need to think a lot more about it. I pointed out several of the problems we can work on, but all will depend on what kind of data we have together. And we just started taking a look at it, and that's why I'm posing it to the community here, which is in the workshop format. Several of us should get together, and I think maybe we should make an open community on this. I'm a huge fan of open innovation. We should make an open community about it as well to make sure we find some of those enablers. Hopefully you can see some of the lessons that we have learned from the software side of things, AI and software together, to see what kind of stack do we need to build for AI for hardware specifications and hardware design, just like we have built for AI for code. We need to build an equivalent stack for AI for hardware, actually code, if I may. Everything is becoming code. Hardware is code as well. So there will be techniques on, obviously a data layer. There will be techniques on internal representations of graphs and others. There'll be techniques on some of the key capabilities. I talked about code understanding, code review. There'll be equivalent capabilities like that for the hardware world as well. And then there'll be applications on top of it, like AI-driven hardware testing and so on. So I could almost visualize having an equivalent stack in the hardware world. But again, this is a tall order and lot needs to come together. I think we are at the beginning of the journey. What I wanted to do is kind of jolt this community and say, I know, I can promise you this. A lot of papers will go on the back end. I know this actually. I've lived that journey as well as and many of you too. But we need to continue to focus on where 4x effort is going compared to the later part, and which I don't see happening yet.
We have time for one last question. I see Marilyn is on, and also Andreas. So, Marilyn?
I would be suspicious of open source hardware repositories as exemplars of commercial hardware. A lot of that's, and I think this is a common problem in AI training data. I can give you a rant on that another time, but I think that in software, it's more representative, not entirely representative, but more representative. But in hardware in particular, the people who are posting their stuff are not the people who are designing star IP.
I think, Merlin, excellent point, and I've heard exactly.
And the other issue is that modules are not architectures, and that stuff is really not out there.
Yeah, Merlin, excellent point, and I would say I've heard exactly the same critique for software, where people will say, well, these are kind of they're not enterprise software. Absolutely right. That critique is not just valid, but absolutely valid. Having said that,
it is a more concerning in the case of hardware, in my view.
I would agree. I think the main answer I will give to that critique is following. We need to crawl before we walk and run. So let's learn from things that may not be perfect yet. I got it. Absolutely got it. But the revolution in AI didn't come together by running right away. Actually, it took a long time for us to get there. And it's not clear to me we have techniques through which we can learn on primitive versions of these yet. And as we get together, then of course there are enterprises which have access to more commercial versions. Whether it is IBM or whether it is Synopsys or whether it is Cadence, and many other companies have more access to the data that you are referring to, and could do more about it. And I'm not saying GitHub is the answer, not at all. Actually, I'm posing that question to see how we can curate some of this together. Maybe some of it can be anonymized and given by some of the industry players. I don't know the total answer to it, but one thing I know is, and you should go to CodeNet and you will see as well, actually, that I think crawling before running is always a good idea. And I am a firm believer in, I don't think we can solve boil the entire ocean. Let's try to get to something that is much smaller and then see where we get to it.
Well, yeah, let me just say that having spent 40 years trying to get companies to cough up some kind of examples, I can tell you it ain't going to happen, okay? They're going to keep their data to themselves.
Okay, guys, Andreas and Mohammed, I hate to stop these excellent discussions because we are already 6 minutes into the next session, but I encourage you to use the chat and hopefully you will stay at the end of today's technical session for the social part where we can join in one of the rooms and continue this interesting discussion. But let me thank you, Ruchir, again for a great talk and very inspiring. So thank you.
Thank you. Thank you for
let me hand over to you, Ellen, to chair the next technical session. So Ruchir, you should unclick yourself from the speaker, and I will unclick myself, and Helen, you can click yourself on the moderator.